250,000 miles from Earth, the silence is absolute. Here, in the void, humanity is constructing its first permanent deep space outpost.
This is a $60 billion gamble on the future of our species.
It is not just a station. It is the most complex machine ever assembled outside low Earth orbit.
Powered by ion engines and autonomous intelligence, it orbits in a delicate gravitational dance.
For the astronauts inside, it is a lifeline suspended in the abyss. Built by a coalition of nations, it represents the apex of global aerospace engineering.
Every bolt, every circuit, every breath of air must be launched on the world's most powerful rockets.
Navigating a near-rectilinear halo orbit that balances the gravity of Earth and Moon perfectly. But how do you build a skyscraper in the sky when the construction site is 250,000 miles away?
This is the engineering story of the Lunar Gateway. To understand the station, we must first understand its unique location, the Near-Rectilinear Halo Orbit.
It is a gravitational sweet spot, allowing constant communication with Earth while maintaining access to the lunar surface.
Unlike the ISS, which hugs the Earth, Gateway is truly in deep space, exposed to the full fury of solar radiation.
The station is not launched whole. It is a puzzle, pieced together over a decade of launches. It begins with power, the Power and Propulsion Element, or PPE. Followed by the heart of the station, the Habitation and Logistics Outpost, or HALO.
Construction began on the ground years before the first rocket ignition. A coordinated effort between Maxar, Northrop Grumman, SpaceX, and international agencies.
At Maxar Technologies in California, the PPE chassis takes shape.
This is not chemical rocketry. It relies on high-power solar electric propulsion.
Using electricity to ionize xenon gas, these engines provide efficient, long-duration thrust. To feed them, massive rollout solar arrays capable of generating 60 kilowatts are installed. Handling this much power requires advanced thermal loops to prevent the electronics from frying.
Every connection is vibration tested to survive the violence of launch.
It all serves as the comms relay, linking the Moon to Earth.
Tanks are loaded with xenon, a heavy inert gas, vital for orbital maneuvering.
The propulsion element is the anchor, the engine room of the entire station.
But an engine needs a cabin. Enter the Halo module.
Built by Northrop Grumman in Arizona, Halo is based on the proven Cygnus cargo spacecraft.
Friction stir welding fuses aluminum panels without melting, creating a bond stronger than the metal itself.
Inside, it is a compact studio apartment for astronauts, packed with life support and logistics. Radial docking ports are machined to sub-millimeter tolerance to accept future visiting vehicles.
The hull is pressurized beyond operational limits to ensure it holds air against the vacuum.
Miles of cabling and plumbing are routed behind the panels before the walls are closed up.
Halo carries its own batteries to survive the eclipse periods when the Moon blocks the sun.
Fans, filters, and scrubbers are installed to keep the air breathable for visiting crews.
The exterior is wrapped in micrometeoroid shielding to stop bullets from space.
Once complete, Halo is shipped to Kennedy Space Center to meet the PPE.
In a departure from tradition, PPE and Halo are joined on Earth, not in space. This integrated stack reduces risk, launching as a single, massive, functional unit.
The ride to orbit is courtesy of SpaceX's Falcon Heavy, chosen for its immense lift capacity.
An extended fairing is required to encapsulate the tall station structure.
£5 million of thrust shatter the Florida calm. Fighting gravity, the rocket pushes the station through the atmosphere.
Side boosters separate, leaving the center core to push towards orbit.
Once in the vacuum, the fairings fall away, exposing Gateway to space for the first time.
The upper stage reignites, sending the payload on a trajectory to the moon.
Gateway separates, beginning its solo journey.
It does not arrive in days. The electric engines spiral the station out over months.
First order of business, unfurling the massive solar wings to catch the sun.
Star trackers and sun sensors orient the craft, guided by software, not joysticks.
The blue glow of the ion thrusters burns continuously, gently altering the velocity.
Engineers on Earth monitor the vitals via the Deep Space Network.
Sensors begin mapping the radiation environment, data critical for future inhabitants. Finally, captured by lunar gravity, it slips into its halo orbit.
Remote commands wake up the life support and thermal systems.
The foundation is set. Now, the expansion begins.
Docking two spacecraft at 17,000 miles per hour is hard. Doing it autonomously near the moon is harder.
Years later, the International Habitation Module, IHAB, approaches. LiDAR sensors scan the docking target, creating a 3D map in real time. Computers make micro adjustments, aligning the ports with millimeter precision.
Contact. The capture latches engage.
Floaters pull the modules together, forming a pressure-tight seal.
Valves open, equalizing the atmosphere between the old and new sections. IHAB is Europe's contribution, built by Thales Alenia Space. It adds critical living volume and advanced life support capabilities.
Following IHAB is Esprit, the refueling and communications hub. Esprit allows the station to be refueled, extending its life for decades.
It also provides the view. Windows offering a 360-degree perspective of the lunar surface.
Japan contributes critical environmental control and battery technologies. With each module, Gateway transforms from an outpost into a station.
But a station this complex needs a caretaker. Enter Canadarm3.
Unlike its predecessors, this arm is smart, It uses AI to plan its own movements.
It can walk end over end, accessing every inch of the station's exterior.
It performs inspections and repairs while the crew sleeps or is back on Earth. It also acts as a cosmic forklift, capturing visiting logistics vehicles. A masterpiece of Canadian engineering, continuing a legacy of space robotics.
This engineering ballet comes with a heavy price tag: $60 billion.
Costs are driven by exotic materials, aerospace-grade titanium, gold plating, and carbon composites.
But the real cost is assurance, testing everything until it breaks, so it won't break in space. Millions of lines of code must be written, verified, and secured against radiation glitches. It funds a global network of ground stations and mission control centers. This investment ripples through the economy, supporting thousands of high-tech jobs.
Money builds the shell, but technology keeps the crew alive. Water is too heavy to launch continuously. We must recycle every drop. CO2 is scrubbed from the air and converted back into oxygen. Outside the Earth's magnetic field, radiation is the silent killer.
Crew quarters are heavily shielded, using water walls to absorb particle impacts.
Psychology matters. Lighting changes to mimic a 24-hour day, grounding the astronauts' circadian rhythms.
Compact exercise gear prevents muscle atrophy in 0G. A digital medical bay allows doctors on Earth to diagnose issues remotely.
Food is pre-positioned by cargo ships, a pantry stocked for months. Waste is collected, compressed, and eventually discarded to burn up in the atmosphere. Gateway is a laboratory, a platform to study the deep space environment. Instruments monitor the sun, predicting solar storms that could threaten Earth. It serves as a staging post for samples returned from the lunar surface. Biological experiments reveal how life adapts to deep space radiation.
Astronauts on Gateway can control rovers on the moon's surface with near-zero latency.
The station comes alive when Orion arrives.
Carrying 4 astronauts, Orion docks, delivering the human element.
The crew floats into Gateway, their home for the next month.
Waiting for them is the human landing system, Starship, or Blue Moon.
2 crew members transfer to the lander, aiming for the lunar South Pole.
The lander departs, leaving Gateway as the orbital sentinel.
Gateway relays their voice and video back to Earth. Mission complete. The lander returns, reuniting the crew in orbit.
It is their safe haven before the long journey home.
Orion undocks, leaving Gateway empty once more. But the moon is just the practice ground. Gateway is the prototype for Mars.
Here we prove the systems needed for a 3-year round trip to the Red Planet. Future Mars transports may assemble here, away from Earth's deep gravity well.
Commercial companies plan to add their own modules for tourism and industry.
It marks the beginning of a true cislunar economy. The engineering challenges are relentless. Extreme heat, extreme cold.
The tyranny of distance means no quick supply runs.
Reliability must be absolute. There is no mechanic to call.
The station must think for itself, surviving communication blackouts. And the humans inside must be tougher than the metal around them.
We built the ISS to learn to live in space. We build Gateway to go places.
It is the gas station, the hotel, and the shipyard of the 21st century.
For the next generation of engineers, it is a beacon of what is possible.
It proves that when nations cooperate, we can conquer the void.
We are no longer visiting the moon. We are staying.
$60 billion. Decades of labor. 1 million miles of wiring.
All to create a tiny bubble of air in an infinite vacuum. From here, the Earth is just a pale blue dot. But the rest of the universe is right outside the window.
The Lunar Gateway is open. This is the Lunar Gateway.